It might seem intuitive that we can predict tomorrow's weather pretty well, but not whether it will rain on Tuesday 3 weeks from now. But we didn't always think that way about the weather. Our understanding of the atmosphere and its patterns was forever changed by the contributions of two exceptional pioneers, MIT professors Jule Charney and Edward Lorenz. Heralds of the modern era of meteorology, Charney and Lorenz, each in his own way, left an indelible mark on MIT and the world. At the height of the Second World War, an unprecedented demand for weather forecasting expertise fueled a nationwide effort to train a generation of meteorologists. Among the young recruits was UCLA graduate student Jule Charney, who had discovered a talent for mathematics at an early age. Anticipating the United States' entry into World War II and encouraged by Caltech professor Theodore von Karman, he signed up for a course in meteorology in 1940, seeing an opportunity to excel. Meanwhile, on the other side of the country at MIT, an aviation cadet and mathematics graduate named Edward Norton Lorenz began his own training in 1942 in the Department of Meteorology, Course 19, marking the beginning of a lifelong connection to the Institute.
I was a graduate student in math at the time our country entered the war. I always been interested in the weather. That is, not professionally. It never occurred to me that I'd ever be studying meteorology, but I always taken an interest in the daily weather. So when an announcement came out, I decided to sign up for the meteorology course, which I thought was something that I could probably do fairly well and perhaps make a contribution to.
When the war ended, Lorenz returned to MIT to complete his master's degree and PhD in meteorology. After graduating in 1948, he stayed on as a research scientist, working with Victor Starr to understand the general circulation of the atmosphere. After publishing a landmark paper on atmospheric energy cycles called Available Potential Energy and the Maintenance of the General Circulation, Lorenz joined the faculty in 1955. His advisor, Victor Starr, had been recruited by Henry Houghton, head of MIT's Department of Meteorology from 1942 to 1969. During his tenure, Houghton transformed the department into a cutting-edge research powerhouse. He founded the training program attended by Lorenz during the war, which grew the department more than tenfold, and oversaw the development of weather radar. Later, in a prescient move, he nurtured MIT's growing oceanography program with help from the Woods Hole Oceanographic Institution, and saw it integrated with atmospheric research. Houghton's vision and guidance laid a far-reaching foundation for scientific advance that would shape the meteorological world for decades to come. While Lorenz was beginning his career in meteorological research at MIT, Jule Charney was beginning to embark on a new adventure of his own. Following the war, Charney had returned to UCLA to complete his doctorate in 1946. His PhD thesis, Dynamics of Long Waves in a Baroclinic Westerly Current, was groundbreaking work which established the mechanism for the emergence and evolution of weather systems and what sets their structure, size, and growth rate. This was an early example of Charney's aptitude for applying mathematics to understanding physical processes.
That really changed my whole attitude toward myself, in a way. It was the first thing that was, I'm anticipating myself, but it was the first example of truly what I thought was truly independent work, nothing that had been assigned to me, and my first experience of that genuine research.
Over the next 2 years, working first as a research scientist at the University of Chicago with Carl Gustav Rossby, who founded the first meteorology program at MIT in 1928, and then as a National Research Council Fellow studying in Oslo, Charney developed his quasi-geostrophic equations, which laid the foundation for modern dynamical meteorology and oceanography. These equations not only allowed large-scale motions of the atmosphere to be analyzed without being overshadowed by noisy effects at smaller scales, they could also be integrated forward in time to predict the weather.
But by then I was already convinced that the thing for me to do was to go to Princeton. Because I was convinced that I I knew how to integrate the equations of motion.
In 1948, Charney took up an appointment at Princeton University's Institute for Advanced Study to work with mathematician John von Neumann and future MIT meteorology professor Norman Phillips on the earliest numerical weather prediction models. Their first calculations were run on the ENIAC computer and published in 1950, and in the years that followed, Charney's theoretical meteorology group demonstrated that the quasi-geostrophic equations were able to reproduce important aspects of the general circulation and even predict the formation of cyclones. This resounding success won widespread acceptance in the meteorological community for numerical weather prediction. The equations also became the theoretical foundation of modern dynamical meteorology and oceanography, permeating every aspect of the field. Building on this momentum, Charney helped to establish the Joint Numerical Weather Prediction Unit in 1954, a collaboration between the U.S. Weather Bureau, Air Force, and Navy. A year later, he had a hand in starting up the General Circulation Research Section of the Weather Bureau. And while this group would eventually become NOAA's Geophysical Fluid Dynamics Laboratory and relocate to Princeton, Charney was already considering a move to MIT.
I would say it brought me back into a meteorological environment.
During an interview, then Provost and Vice President Jule Charney asked Charney what could be done to improve the meteorology department. Having always been impressed by Ed Lorenz, then still a research scientist, Charney replied that the first thing to do would be to promote Lorenz and his advisor, Victor Starr. He also reached out to recruit his Princeton colleague, Norman Phillips. Lorenz and Phillips were duly offered faculty positions, and Charney likewise joined MIT to direct the Atmospheric and Ocean Dynamics project in 1956. Charismatic and open-minded, Charney had a knack for bringing people together. He quickly established an informal seminar series on geophysical fluid dynamics, a tradition that would continue for 22 years, attracting experts from around New England in the fields of meteorology, oceanography, geophysics, and applied mathematics. During his 25 years at MIT, Charney mentored countless students and made profound, lasting impacts on the field through groundbreaking research on such diverse topics as the stability of atmospheric and oceanic flows, the formation and evolution of weather systems and hurricanes, oceanic boundary currents, how large-scale planetary waves extend up into the stratosphere, the formation of deserts, and how westerly winds can flip between banded and wavy patterns. He also continued to play a role in the establishment of critical weather-related initiatives, including the Global Atmospheric Research Program, an observational effort improving numerical weather prediction. One of Charney's last contributions was a pioneering study conducted for the National Academy of Sciences. The 1979 Charney Report was one of the earliest modern scientific assessments of global warming. He estimated that a sustained doubling of atmospheric CO2 would lead to a surface temperature increase of between 1.5 and 4.5 degrees centigrade, a range that has been vigorously debated and has stood the test of time. Though Charney and Lorenz shared a similar background in mathematics and a mutual admiration for one another, the two never worked together directly during their time at MIT. Nevertheless, their research interests intersected, and the development of numerical weather prediction facilitated by Charney's equations carried Lorenz's research into atmospheric dynamics forward. In 1967, he published The Nature and Theory of the General Circulation of the Atmosphere, a treatise now considered a classic work of scientific literature. By that time, however, a new, exciting research direction had begun to occupy Lorenz's attention. In 1963, after noticing that very slightly different initial conditions, due to roundoff errors generated by his LGP-30 computer, resulted in rapidly diverging solutions, Lorenz published a landmark article on chaos theory, the idea that nonlinear systems such as weather are practically unpredictable despite their deterministic evolution.
I found this very exciting because this implied that if the atmosphere behaved this way, then long-range forecasting was impossible, because we certainly don't measure things as accurately as that. This is really what got me interested in predictability.
The Lorenz system, 3 differential equations that relate the motions of a fluid layer warmed from below and cooled from above, is one of the fundamental systems studied in chaos theory. These simple equations revealed startling behavior, which led Lorenz to an important insight. Though the chaotic solutions never repeat, they nevertheless tend to look very similar, even when starting from a range of initial conditions. Run many times, the solutions trace out a previously unknown mathematical object that Lorenz termed a strange attractor. This fractal set of solutions introduced new tools to analyze nonlinear chaotic systems, helping to answer questions like why some weather pattern geometries are common, while others seem never to occur. Continuing his study of predictability, Lorenz demonstrated in 1969 that the nonlinear interaction among motions of many different scales could lead to loss of predictability even when the model is perfect and the initial errors are vanishingly small.
It came really as almost a shock when I realized that it was behaving this way. As we look at it now, we think this is what we should have expected all the time, but I never had.
This theory was popularized as the butterfly effect, the idea that small changes can have large consequences. Lorenz's discovery not only revolutionized the understanding of fluid turbulence and weather, but also led to advances in mathematics, the natural sciences, and engineering. Lorenz was a vital member of MIT for over 60 years, serving as the head of meteorology from 1977 to 1981. Much beloved as an instructor and mentor, he was repeatedly honored as Best Teacher of the Year by MIT graduate students, and he continued to conduct research and give lectures well after becoming a professor emeritus in 1987. He passed away on April 16, 2008, and 3 years later, MIT created the Lorenz Center in his honor, dedicated to furthering the basic understanding of climate science. By comparison, Jule Charney's tenure at MIT was relatively brief. After a fierce battle with cancer, he died on June 16, 1981, just 2 years after publishing his pioneering report on the connection between carbon dioxide and climate. Even so, his impact on MIT and around the world stands shoulder to shoulder with that of his colleague and friend, Ed Lorenz. Born 100 years ago, both men fundamentally reshaped the science of meteorology during their lifetimes. Charney saw the dawn of numerical weather prediction and its widespread influence on nearly every aspect of atmospheric and oceanographic research. Lorenz shifted our basic conception of weather and climate from deterministic phenomena to chaos, and this insight suggested new ways to examine nonlinear chaotic systems, an impact that spread outward from meteorology to transform a host of other disciplines. But perhaps their most enduring legacy is the community of people trained, taught, and inspired by Jule Charney and Ed Lorenz.
What I discovered after moving to MIT was that what I did enjoy mostly was working more individually with graduate students on thesis research and research problems. Because I find that my own work is greatly enhanced and becomes much more enjoyable when I can discuss it with other people.
Today, the study of atmospheric science continues at MIT in the wider context of EAPS, the Department of Earth, Atmospheric, and Planetary Sciences, formed in 1983 from the merger of meteorology and earth sciences. Now, 100 years later, the program in atmospheres, oceans, and climate within EAPS celebrates and honors the lives of Charney and Lorenz as their students and their students' students continue to walk in their footsteps, exploring the myriad reverberations of the work they set in motion.